Welcome to our deep dive into two fundamental concepts in physics, work and power. These ideas are not just confined to textbooks, they're all around us, from lifting groceries to powering your smartphone. In this video, we'll break down what work and power mean in the context of physics, explore their formulas, and see how they apply to real-life situations. Whether you're a student, a curious mind, or someone brushing up on the basics, you'll find this journey both enlightening and practical. Let's start by understanding why these concepts matter and how they connect to the energy that drives our world. Everyday language, work might mean any task or effort, but in physics, work has a specific definition. Work is done when a force causes an object to move in the direction of that force. For example, pushing a box across the floor involves work, but holding a heavy box still does not. The key is movement in the direction of the applied force. This precise definition helps us measure and calculate how energy is transferred in various situations, making it a cornerstone of physics. Formula for work is straightforward. Work equals force multiplied by distance, or W equals F times D here. F stands for the force applied and D is the distance over which the force acts, both in the same direction. If you push a cart with a certain force and it moves a specific distance, you can calculate the work done. This formula allows us to quantify the energy transferred by force, making it easier to analyze different physical scenarios. Physics, the unit of work is the joule, symbolized as J. 1 joule is the work done when a force of 1 Newton moves an object 1 meter in the direction of the force. This unit helps standardize measurements, making it easier to compare different scenarios and calculations. Understanding the joule is essential for grasping how energy is measured and transferred in the physical world. Let's look at some everyday examples of work in action. When you lift a backpack off the ground, you're doing work against gravity. Pushing a lawnmower across the yard or pulling open a heavy door are also examples. In each case, a force is applied and the object moves in the direction of that force. These simple actions help illustrate how the concept of work is woven into our daily routines, even if we don't always realize it. Might surprise you, but not every effort counts as work in physics. If you push against a wall and it doesn't move, no work is done even if you feel tired. The same goes for holding a heavy object still. In both cases, there's force, but without movement in the direction of the force, the work done is zero. This distinction is crucial for understanding how energy is actually transferred. Work and energy are closely related in physics. When work is done on an object, energy is transferred to or from that object. For example, lifting a book increases its potential energy, while pushing a sled transfers kinetic energy. This relationship helps us understand how forces change the energy of objects and systems, forming the basis for much of classical physics. Work can be positive or negative depending on the direction of the force and movement. If you push a box forward, the work is positive because the force and movement are in the same direction. But if you try to slow down a moving object like catching a ball, the work you do is negative as your force opposes the motion. This distinction helps explain how energy can be added to or taken from a system. Now let's shift our focus to power. While work measures the amount of energy transferred, power tells us how quickly that work is done. In other words, power is the rate at which work is performed. This concept is crucial in everything from engines to electronics, helping us understand not just how much energy is used, but how fast it's used. Formula for power is simple. Power equals work divided by time, or P equals W/T here. P stands for power, W for work, and T for the time taken to do the work. This formula helps us compare how efficiently different machines or people can perform tasks, making it a key concept in engineering and daily life. Power is measured in watts, symbolized as W. 1 watt is equal to 1 joule of work done per second. This unit is named after James Watt, the inventor who improved the steam engine. Understanding watts helps us compare the power of everything from light bulbs to car engines, making it a practical and widely used measurement. Power is all around us in daily life. When you run up a flight of stairs quickly, you use more power than if you walk slowly, even though the work done is the same. Appliances like microwaves and hairdryers are rated by their power in watts, showing how fast they can do work. These examples make the concept of power easy to spot in our routines. It's important to distinguish between work and power. Work measures the total energy transferred, while power measures how quickly that transfer happens. Two people might do the same amount of work, but the one who finishes faster uses more power. This difference is crucial in fields like sports, engineering, and even in our own bodies. Machines are often rated by their power. For example, a car engine's horsepower or a blender's wattage tells us how quickly they can do work. High-power machines can accomplish tasks faster, which is why power ratings are so important in engineering and product design. Understanding this helps us choose the right tools for the job. Efficiency is closely linked to power. A more efficient machine does more useful work with less wasted energy, often in less time. This means higher efficiency can lead to higher power output for the same energy input. Engineers strive to design machines that maximize both power and efficiency, saving time and resources. Humans also generate power. For example, a professional cyclist can produce several hundred watts during a sprint, while an average person might generate about 100 watts when riding a bike steadily. These numbers help us understand our own physical capabilities and compare them to machines. Athletes constantly deal with work and power. Sprinters, for example, must generate high power to accelerate quickly, while endurance athletes focus on sustaining work over time. Coaches use these concepts to design training programs that improve both strength and speed, optimizing performance. Technology relies heavily on power. From smartphones to computers, the power rating tells us how fast devices can process information or perform tasks. Higher power often means faster performance, but it can also mean more energy consumption. Balancing power and efficiency is a key challenge in tech design. Nature is full of examples of work and power. Waterfalls do work as water moves rocks and carves valleys. Lightning releases immense power in a split second. Even animals like cheetahs sprinting or birds flying demonstrate these concepts in action. Observing nature helps us appreciate the universality of work and power. Let's walk through a simple calculation. Suppose you push a box with a force of 10 newtons over a distance of 5 meters. Using the formula W equals F times D, the work done is 10 times 5 equals 50 joules. This step-by-step approach makes it easy to apply the concept to real problems, whether in homework or daily life. Now let's calculate power. If you do 50 joules of work in 10 seconds, power is P equals W slash T equals 50 slash 10 equals 5 watts. This shows how quickly energy is transferred. Practicing these calculations helps build a strong foundation for more advanced physics topics. Sometimes the force isn't applied in the exact direction of movement. In these cases, only the component of the force in the direction of motion counts. The formula becomes W equals F times D times cos theta, where theta is the angle between the force and movement. This adjustment is crucial for accurate calculations in real-world scenarios. When you apply brakes to a moving bicycle, you do negative work. Your force opposes the motion, removing kinetic energy from the system. This concept explains why brakes heat up. They're converting kinetic energy into heat through negative work. Power isn't always constant. Instantaneous power measures how fast work is being done at a specific moment. For example, a sprinter's power output spikes at the start of a race. This concept is important in analyzing changing systems and understanding peak performance. Average power is calculated over a period of time. If you do a certain amount of work over several seconds or minutes, average power tells you the overall rate. This is useful for comparing performances or evaluating machines over longer tasks. In electricity, power is the rate at which electrical energy is used or produced. Light bulbs, for example, are rated by their power in watts. A 60-watt bulb uses more energy per second than a 10-watt bulb. Understanding electrical power helps us use energy more efficiently at home and in industry. Mechanical power refers to the rate at which work is done by machines or moving parts. For example, a crane lifting a load or a conveyor belt moving boxes both involve mechanical power. This concept is key in engineering, construction, and manufacturing. Vehicles like cars, trains, and airplanes are rated by their power output. More powerful engines can move heavier loads or reach higher speeds. Understanding power helps engineers design safer, faster, and more efficient transportation systems. Construction sites are full of examples of work and power. Cranes lifting steel beams, workers using jackhammers, and trucks hauling materials all involve energy transfer and power output. These concepts help ensure projects are completed safely and efficiently. Renewable energy sources like wind and solar power are measured by the amount of power they can generate. Engineers calculate how much work these systems can do over time, helping us transition to cleaner, more sustainable energy solutions. Our bodies are remarkable machines. Muscles do work when we move, and our metabolic rate measures the power our bodies generate. Understanding these concepts helps athletes train, doctors diagnose, and everyone appreciate the energy we use daily. The study of work and power has a rich history. Scientists like James Watt and Isaac Newton laid the groundwork for our modern understanding. Their discoveries revolutionized industry and science, showing how fundamental these concepts are to progress. Factories and industries rely on work and power to operate machinery, move goods, and produce products. Measuring and optimizing these factors helps businesses save energy, reduce costs, and increase productivity. Not all power is used efficiently. Friction and resistance cause power losses in machines and systems. Engineers work to minimize these losses, improving efficiency and saving energy. Understanding where power is lost helps us design better technology. Safety is a major concern wherever work and power are involved. Machines with high power can be dangerous if not handled properly. Understanding the principles of work and power helps prevent accidents and ensures safe operation in homes and workplaces. Space missions require careful calculations of work and power. Rockets must generate enough power to escape Earth's gravity, and spacecraft systems rely on efficient power management. These challenges push the boundaries of engineering and science. Even in art, work and power play a role. Sculptors use force to shape materials, and kinetic art relies on moving parts powered by motors or wind. These creative applications show how physics concepts inspire and enable artistic expression. When shopping for appliances, you'll notice power ratings in watts. These ratings help you compare how quickly devices can do work and how much energy they'll use. Choosing the right power level can save money and energy in the long run. Communication systems from cell towers to satellites rely on power to transmit signals. The efficiency of these systems depends on how much work is done to send information over distances. Understanding power helps improve connectivity and reduce energy use. Medical devices like X-ray machines and MRI scanners use significant power to operate. Understanding work and power ensures these tools are safe and effective, helping doctors diagnose and treat patients more efficiently. The way we generate and use power affects the environment. Burning fossil fuels for power releases greenhouse gases, while renewable sources offer cleaner alternatives. Understanding power helps us make better choices for a sustainable future. Robots perform work and require power to move, lift, and interact with their environment. Engineers design robots to maximize efficiency, balancing power needs with battery life and performance. This field is rapidly advancing thanks to our understanding of these physics principles. Entertainment systems, from concert speakers to amusement park rides, rely on work and power to create experiences. High-powered equipment delivers sound, light, and motion, making events more exciting and memorable. Let's recap what we've learned. Work is the transfer of energy through force and movement, measured in joules. Power is the rate at which work is done, measured in watts. These concepts are everywhere, from nature to technology, sports to art. Understanding them helps us make sense of the world and improve the way we live and work. Work and power are more than just formulas, they're the foundation of how things move, change, and function in our universe. By understanding these concepts, we gain insight into everything from the smallest machines to the largest natural forces. Keep exploring and you'll find that physics truly is everywhere, shaping the world in fascinating ways.